क्या हुआ? ये सारे लोगों को फिर से बुलाना पड़ेगा। इन्हीं का ही तो क्लास है ना, आज ट्यूसडे है। ट्यूसडे मेरा, हाँ। अरे सर, ये जो नया रूटीन बना था ना अपने, अभी जो बोल रहे थे, मैं सो रहा था सर 8-10, या मैं तो वैसे ही घर में तो वैसे ही सोता हूँ 8-10-15 फिर ही उठता हूँ। तो मैं वो रूटीन अचानक देखने लग गया है, ये नया रूटीन आया है, देखता हूँ। देखिए, तो उस दिन ट्यूसडे ही था ना, मेरा आँख पर गहरे ट्यूसडे मॉर्निंग में, एक ट्यूसडे मेरा एक ही क्लास था। ये ट्यूसडे 10 बजे क्लास था, ये मॉर्निंग 9 से ही तो क्लास दिया है। तो देखा वो भी ये लोग का है, मैं इमीडिएट उठ गया तो जल्दी से मुंह से धोकर बाथरूम जाके खा पी के देखिए, रात 1 बजे तक, रात को कौन देखता है? मैं तो 12 बजे के बाद। नहीं नहीं, ट्यूसडे ट्यूसडे से मंडे रात को रूटीन भेजा, तो मंडे रात 12:30-1 बजे को रूटीन भेजा। तो अभी इतना रात को तो रूटीन देख के कोई बैठा नहीं रहेगा। जिसने बनाया उसको तो ठीक है, पता होगा। हाँ, दूसरा लोग थोड़े देखना रहता है। हाँ, और उस दिन तो मैं तो जनरली इतना सुबह को मोबाइल देखता भी नहीं, उस दिन किसी तरह किसी लिए देख रहा था, नहीं तो वो क्लास तो मिस हो जाता मुझसे। फिर भी मैंने कर लिया। और स्त्री लोगों को ही पता नहीं, अरे क्या बोल रहा है, सुबह सुबह हम लोगों का भी तो कभी क्लास नहीं रहता। ये शाम को मतलब इसको काम करने का टाइम नहीं है, और ये लोग क्यों, इन लोगों का कोई एग्जाम है 1 बजे से, देवाश्री का एग्जाम, इसलिए ये लोग क्लास आ ही नहीं रहे। क्या बात है, ये 15 मार्क के एग्जाम के लिए सेशनल नहीं, ऐसे ही ये लोग क्लास नहीं करेंगे या कोर्स खत्म हो गया है। ओके, पंछी आ गई है। ओके पंछी, so finally you got time to attend, huh?
Network is not.
You have network
Good,
problem.
that's why. Yes, sir.
Okay, anyway, so I will start with you. I mean, you are the student here only. Okay, so did you attend the last class about Joule-Thomson effect? Let me share. So we are doing the Joule-Thomson porous plug experiment in the last class. So did you attend that class?
I didn't join. Sir, no, sir.
You did not.
No, I did not.
Okay, so if you did not, then okay. So Joule-Thomson porous plug. So I am not going to explain everything. I will just give it a revise. And so what we found out and what we have to do next. So in 5-10 minutes I will revise, and then we will go to today's topic. Okay. So Joule-Thomson experiment, what happens that in this experiment a gas, okay, a gas is allowed to pass through a porous plug. Porous plug is here in this figure. If you can see this figure 10.2, in this figure, so this is the gas. Okay, so this is a piston, A is a piston, and here is a B is a piston. Okay, B, capital B is a piston, and there is a porous plug which is in touch with the piston. Porous plug is called G, small g, and that is in touch with the piston B. Okay, so what you do here is that there is a gas here. Okay, this gas is allowed to pass through the piston, sorry, allowed to pass through the porous plug. Porous plug means it's a medium through which has very small pores, okay, pores or paths like wool, cotton, silk, those type of things. So this G thing, it's called a porous plug, and it may be made of like wool, cotton, and something like that. Okay, so that gas or liquid or fluids that can pass through the very small and narrow paths through this. Okay. Okay, so what will happen? So you apply some pressure here on the piston A, okay, highly compressed to pressure A, okay. So you apply a pressure on the gas, apply pressure on this gas with the help of this piston, okay. And suppose the applied pressure is PA, okay. And the other piston, this piston B will be subjected to a pressure of B, PB, okay. Now, once the gas gets a high pressure from the piston A, so the situation will be something like this. This particular gas, VA is the volume of the gas. This particular gas, which was initially between the piston A and piston A and this porous plug G, will be expanded, and it will be between the porous plug G and the piston B. Okay, the gas will be expanded and it will take a position between this piston and the porous plug. Okay, so are you understanding? The gas, initially this gas will pass through the porous plug, and finally after all the gas has passed through the porous plug, so the gas will be in a new position. And earlier you see the porous plug and the piston were touching each other. Now the porous plug is the porous plug and the piston B were touching each other earlier, but now the porous plug is in touch with the piston A, okay, and the gas has now a new volume. Earlier volume of the gas was VA and the new volume of the gas is VB, okay. Okay, so now what happens? So we have to consider this, like how much work has been done by the piston and how much work has been uh, done on the done by the piston A, and how much work has been done by the gas on the piston B. So these things you have to consider. Then you have to net work done. So what is the net work done in this process? That also you have to consider. Okay, and then you have to consider this quantity called change in internal energy. Okay, so internal. So earlier, suppose the internal energy was UA, and later after the gas has expanded through the porous plug, so maybe the later the internal energy is UB, then what is the change in internal energy that you have to consider? Okay, so what is the net change in internal energy? That is UA minus UB. Okay, okay, now what we are going to show about this experiment is that there is actually a change in temperature. A change in temperature when the gas is allowed to pass through a porous plug like this. Okay, so how this temperature changes, that we will derive today. Okay, so okay, and this process is carried out adiabatically. What is adiabatically again? So there is no heat involved in this thermodynamic process. Okay, you are neither adding any heat nor releasing any heat from the system. Okay, that is the thing. So yeah, so that is the thing. No heat is involved during this expansion of the gas. Therefore, you go back to first law of thermodynamics. So dq is equal to du plus dw. So it is an adiabatic process. So dq is equal to 0. So dw is this one, net work done Pb Vb minus Pa Va, and the change in internal energy is Ub minus Ua. Okay. Okay, here it is written Ua minus Ub, but it should be actually Ub minus Ua. Okay. So from this equation, from first law of thermodynamics, so dq is 0, so du is Ub minus Ua, dw is Pb Vb minus Pav. So Ua plus Pav equal to Ub plus Pb Vb is constant, equal to H. Okay. So what is H? H stands for enthalpy. Okay, enthalpy is the total heat content of a system. So it is one of the thermodynamic potentials that we earlier learned. So H equal to U plus PV. Okay, so UA plus PA equal to UB plus PB. That means HA equal to HB. HA plus HB equal to HB means the process takes place at constant enthalpy. Okay, so this thing which we are just Joule-Thomson expansion of the gas takes place in a takes place under constant enthalpy. Okay, yeah, and so it's an adiabatic process, and since the process is adiabatic, if you consider net work and change in internal energy, you will eventually find that this process takes place at constant enthalpy, and that is why this process is also known as isenthalpic process. Okay, hence Joule-Thomson experiment or expansion. Hence, in a Joule-Thomson experiment or expansion, the enthalpy of the gas remains constant. Okay, the enthalpy of the gas does not change. Okay, so anyway, that is a one thing. Another thing is after the gas is expanded, let me annotate here. See, initially VA is the volume of the gas, finally VB is the volume of the gas. So you see this VB volume is greater than VA volume. Okay, so what happens? Volume of the gas expands. Okay, but volume of the gas is expanding, but at the same time if volume of the gas expands, then what will happen? The temperature of the gas will come down. Okay, or simply temperature changes. So in Joule-Thomson's experiment, let me type it here. Let me type it here. I hope you are able to see. Okay, I hope you can see this. So what I have written is in Joule-Thomson experiment, there is a change in temperature of the gas after it expands through the porous plug. Okay, so after it expands through the porous plug, the temperature of the gas will change. Now this change is like if the temperature increases or decreases, that is what we need to check. Okay, let us try to check now if this temperature increases or decreases. Okay, actually I have this note. Let me see how to write this. Okay, my note is somewhat different from this given. Okay, can you just wait for a minute? I will try something new. Just give me a minute, okay? Just give me a minute. I will try a different thing. I will try to use this tablet to write some equations and show you. Okay, let me see if I can do it or not. Just give me 2 minutes. Let me see if it works or not. No, it does not work here. So, okay, just a minute. No, it does not work here. So just give me 2 more minutes. I will try to see. Okay, let me see if it works here or not. So standard pen thickness. So can you see what I'm writing something? Joule-Thomson. So I am writing on the tablet, which you can see in the laptop. Porous plug experiment. Okay. So now we will show. So are you seeing? Can somebody confirm me? Are you seeing what I'm writing?
Yes, sir.
Okay, good. So we will show that there is a change in temperature after the gas passes through the porous plug. My handwriting may not be very good, but I hope still you will be able to understand. Okay, so how will you show that? Okay, change in temperature. Okay, so change in temperature is what we are going to study. So consider that enthalpy is a state function. Okay, consider enthalpy to be a state function such that H is a function of pressure and temperature. So enthalpy H, what we'll assume. So I want to make this to pen a bit thicker shape recognizer. So uh, pen options, medium, thick. Okay, thick. Okay, so we will first consider that this enthalpy is a function of pressure and temperature. Okay, so enthalpy is a state function. Okay, state function. Suppose it depends on values of pressure and temperature. Remember, this Joule-Thomson experiment, which you have studied, is actually a constant enthalpy process. Okay, so from that point of view, we have to start our derivation. So what are we going to derive? We are going to derive that there is a change in temperature in a Joule-Thomson experiment. Okay, so for such so dH. So if enthalpy is a function of pressure and temperature such that H is equal to H PT, then how we can write these functions? We can write them like this dH. Okay, just show people myself. Okay. dH dP. So state functions can be written like this. These things we have already discussed such things previously. Okay, state functions can be written like this, written in this form. Okay, suppose this is some equation number one, give it some equation number one. Okay, the heat capacity at constant pressure. Now heat capacity at constant pressure, specific heat capacity at, I will give you the note. Okay, this is just for class demonstration. Heat capacity at constant pressure is given by dH dt at constant P. Okay, so this is nothing but specific heat at constant pressure. So specific heat is, so in earlier cases we write it as dq over dt at constant P. But dq is the amount of heat supplied to a system, to a thermodynamic system. But enthalpy is, once again, it is the total heat content of a thermodynamic system. Okay, so q can be replaced by h. So directly this quantity we are writing as, this as specific heat. Okay, Cp. Cp is dH over dt at constant P. Therefore, how we can write equation 1? Equation 1 can be written as dH equal to dH over dP constant dP plus this one can be written as Cp dt. Okay. Suppose this is equation number 2. Okay. Now difference. Okay, sorry. Also from definition of enthalpy. Okay. Also from definition of enthalpy. So this one, this equation, what we have derived, this is considering enthalpy to be a state function. State function means which depends on pressure and temperature. But by enthalpy's own definition, we can write enthalpy change dH as TdS plus VdP. TdS plus VdP. So these things we have learned in thermodynamic potentials. Okay, when we are studying about thermodynamic potentials, we are learning about these things. Okay, now what this thing we have got earlier. Okay, so what we will do is differentiating this equation with respect to pressure at constant temperature. Differentiating this equation with respect to pressure at constant temperature. Since temperature is constant, so the T term will be outside. Differentiating with respect to pressure. Okay, so pressure dP term is here, so dP term will get cancelled, so we will have only the volume term here. So it will be dH over dP at constant T is equal to T ds dP at T plus V. Okay, differentiating this equation at constant, differentiating this equation with respect to pressure at constant temperature. Okay, that is how we can write it. Then okay, then from one of Maxwell's thermodynamic relation, SPTV, SPTV, SPTV. So it will T is P. There will be negative sign. Okay, so we can also, this is one of Maxwell's thermodynamic relations. Okay, so in place of SP at constant T, we will substitute this value with this value. Okay, so let us see what happens, what we get. So dH over dP at constant T equal to, so ds dP at T, ds dP at T, we can write it as minus dV dt, minus dv dt at constant p plus v. We can write like this, okay? Okay, so dh dp. Okay, then go back to equation number one. Okay, so now go back to equation one. So equation one, so we have just found out the value of this first part, dh over dp at constant t. Okay, so dh over dp at constant t. So I will go back to equation one again and rewrite the equation one. Okay, so in that case, equation one can be written as dh equal to bracket. So this value minus t dv dt at constant p plus v, and then dp. Sorry. Uh, okay, this is nothing. Okay, this is nothing. This is plus dp cp dt. So this is how finally we can write the equation 1s. Okay, equation 1. So yeah, so equation, sorry, not equation 1, actually it is equation 2. Equation 2 is in fact derived from equation 1. So sorry, I will write it as equation 2, not equation 1. Okay, so both are same, just like, okay. So now enthalpy is constant in Joule-Thomson experiment, okay, expansion, okay. So in Joule-Thomson experiment, okay, in JT expansion, okay, Joule-Thomson, I am writing that in short as JT. In Joule-Thomson expansion, enthalpy is constant. Okay, if you attended the last class and today also, earlier, I mean, in the first part, I was discussing about this Joule-Thomson experiment, where we have learned that Joule-Thomson expansion is actually a constant enthalpy process. In Joule-Thomson enthalpy is constant. If enthalpy is constant, that means the differentiation term of enthalpy will be equal to 0. Okay, dH will be equal to 0 when enthalpy is constant. Okay, so if dH equal to 0, suppose this equation 2 you have simplified, then you get equation 3. So come back to equation 3 and that will be 0 equal to, write down whatever you have, minus t. So we'll get an expression like this. Okay, uh, so dH, okay, sorry, it is 0. Okay, we will get something like this. Dt over dp. So what we need to find out, we need to find out dt minus, okay, so from here, from this equation, so this is equation 4. So so if you want, you can give this equation some number, otherwise no need to give some number. Okay, so from this equation 4, find out the expression for dt over dp. Okay, so find out the expression for dt over dp from this equation 4. And we represented the dt over dp by this quantity, something called mu. Okay, mu is equal to dt over dp, and then you find the rest of the values. 1 by cp t dv dt p minus b. Okay, so where this quantity mu is called something Joule-Thomson coefficient. Okay, so I'm writing this Joule-Thomson as like Joule-Thomson coefficient. Okay, so yeah, so finally we get this expression by making enthalpy equal to zero. Why enthalpy change equal to zero? Why enthalpy change equal to zero? Because this Joule-Thomson experiment, as we have already learned, is that a constant enthalpy process. That means H is constant. If H is constant, therefore dH will be equal to zero. Okay. So next, let me check, and we will define this quantity mu. Okay. Okay. So dP. Now let us check this term dP. So how the temperature changes, that is what we are going to find out from this equation. So this is equation 5 maybe. So how this temperature changes, that we will try to find out. So dP. So dP is the change in pressure. Okay. So what happens? So dP. So what happens to this change in pressure in this particular case? The change in pressure is negative. Okay, so dP, the change in pressure. Okay, dP is the change in pressure. This is a negative quantity. Okay. So why negative quantity? Because if you go back to the so what about the initial pressure? Because if you so initially today I have mentioned that the pressure PA, okay, PA, which is the pressure applied on the piston, and there was a pressure which is the pressure which the gas applies on the piston B. This is the pressure applied on the piston A, and this is the pressure applied on the piston B. So in this case, actually PA was greater than PB. The pressure which was applied on the piston A was greater than the piston B. Therefore, this change in temperature means the final pressure is smaller than initial pressure. Okay. So this is the first page, which here I have done, and now the second page. Okay. So that means, let me write it down. That means final pressure is, oh, not that means, sorry, not that means, since, I will write here, since final pressure is uh, lower than initial pressure, so dP is a negative quantity. Okay. So dP is a negative quantity since, yeah, since final pressure is less than initial pressure. Okay. So now you see mu. Okay. So mu is, so that is what we defined, the Joule-Thomson coefficient. Mu is dt over dP. So dt over dP. Okay. So what we have found out just now, that dP is negative. dP is negative. Okay. Therefore, if mu has to be a positive quantity, then, so I will write it down here. So if mu has to be a positive quantity, dt should be a negative quantity. So have you understood this? So dP is negative, that we have just seen, because final pressure is less than initial pressure. Now, if mu, this Joule-Thomson coefficient has to be a positive quantity, in that case, what should happen? dt should also be a negative quantity, because if you divide one negative quantity with another negative quantity, we will get a positive quantity, okay? Because negative by negative is a positive quantity, okay? So dP is negative, but if mu has to be positive, okay, so mu positive, dP is negative, in that case, dt should also be negative, okay. If dt has to be negative, then what is the case? The final temperature. So the final temperature, so the final temperature should be less than initial temperature. Okay, since dt is a negative quantity, in that case, the final temperature should be less than the initial temperature. Okay, you understood this? That means if final temperature is less than initial temperature, the temperature falls. So this is actually the whole note I have written here. The temperature falls after the expansion of the gas. After the expansion of the gas. Okay, so have you understood? This is the important thing. So how the temperature changes after Joule-Thomson expansion. Joule-Thomson expansion is again the expansion of the gas through the porous plug, and after the gas has expanded through the porous plug, its temperature will actually fall. Okay, so fall means the temperature will be reduced, and temperature, so that is what we needed to show it now. So that is what we needed to show, if there is any change in temperature after Joule-Thomson expansion of a gas through a porous plug. Okay, so that is how you can do the derivation actually. So considering starting from enthalpy, consider enthalpy to be a function of pressure and temperature, then these considerations, then come to the direct exact value of enthalpy. So from here you find out change in enthalpy, like d. Then these two quantities you have to find from equation 1. This is Cp and this is dH over dP at constant T. You find these expressions, then mu, find out the expression for mu, which is dt over dP. And then if mu is a positive, dP is a negative quantity because it's the reduction in pressure. Initial pressure is greater than final pressure. So mu, and if mu has to be positive, dP is negative, so dt has to be negative. Okay, if dt has to be negative, that means your temperature of the gas will fall after the Joule-Thomson expansion. Okay, so that's it. That is what we had to show. So how the temperature changes after Joule-Thomson expansion of the gas. Okay. Okay, so with this, I think it's done for today. So we have 3-4 more topics that we'll learn in the upcoming classes. So I am stopping the share. So I hope all of you have been able to catch it. And I will end the class here. And tomorrow morning also we have a class from 10 a.m. Okay. So in tomorrow's class, we will see the virial equation or some other thing we'll discuss about. Okay. So also keep an eye on Google Classroom. From time to time, I have been uploading the study materials. Okay, most of the study materials have been uploaded. So keep an eye there and get your notes from there. Okay, so I will end the class here and thank you all for your attendance.